So thank you very much. I'd also like to thank Peter Weibel and also the staff from ZKM for all their wonderful work getting me from Australia to here. That's no mean feat, let me tell you. But I've conquered the jet lag and I'm feeling good. As Yasmin mentioned, this talk stems from a project that I'm currently doing with Adrian MacKenzie, who unfortunately couldn't be here. He was going to come to this conference, but couldn't. And so some of the project's in very early stages, but some of the thinking is certainly collaborative. I'll own all the mistakes, but to say that the ideas are very much something that's we're working together on. Okay, so amid a flood of images enabled by the massification of black box mechanisms, cheaper display options, and for the first time, aggregated mobile storage solutions, in 1896, not now, Henri Bergson described both the universe and matter as an aggregate, or ensemble in French, of images. This ensemble of images I call the universe, or I call matter the aggregate of images. Bergson was, of course, writing in the midst of the popularisation of photography, driven in part by Kodak's 1888 release of its first box Brownie camera, and perhaps with the foresight that by 1900 there would already be more than 100,000 of these sold. Matter and memory, from which Bergson's claim is drawn, is, among other things, an exploration of the techno-ontogenetic relation between perception and the image. Yet his refusal to distinguish between the empirical world and aggregates of images has proven to be somewhat prescient. Glance through any data science article or developer's blog post on machine learning and you'll quickly glean that images are discussed in purely quantitative terms that indicate what is currently of importance is precisely aggregates of images. Millions of training examples and an endless stream of new impressions, or we trained for a total of 50 million frames, are typical phrases scattered across research reportage on contemporary forms of artificial intelligence. These forms of AI are driven by machine learning architectures and often treat images as a material baseload that might power new visions for automated and autonomous decision-making and task performance. Although we've become used to the mathematical sublime underpinning the term big data, we've paid less attention to the imagistic nature of all this data. What operative roles do these aggregates of images and new modes of observing and seeing derived from them play in the way that AI assemblages form technically, socially, and aesthetically? Bergson's account of images may be helpful here. It locates perception in neither a viewer nor external stimuli, but rather as emergent actions of and from the flux of image signal ensemble. Considered as a universe, this infinite flux of images is an assembly of pathways that can be traversed in many different ways. Perception, then, is both a traversal of images and, since all movements modulate the flux of the entirety of image aggregates in some way or another, perception simultaneously transforms this flux by extracting a set marking a specific point of prehension of that flux. In Gregory Flaxman's terms, perception constitutes that dark surface on which the ceaseless flow of images is momentarily captured and thereby transformed into a set. Both the quanta of images and their particular modes of aggregating and being traversed lay stake to the claim that, together, image aggregates and machine learning architectures straddle the empirical and simulated worlds. Here, the question of the ensemble or the relationality of aggregation becomes important. Further, and staying with Bergson, acts of observation, or for him perception, are nothing more than provisionally stabilised derivatives of the image ensemble. They don't differ from the ensemble except in their connection to potential movements or actions of the observer. In what way, then, do machine learning architectures derive their capacity to see, to recognise features and pattern by traversing image aggregates along certain pathways, temporarily stabilising modes of multiple and distributed observation via vectors, filters, feed-forward and back-propagation processes? Via a limited uptake of Bergson, and I'm aware that he is quite anthropocentric in his focus on perception, but trying to put that aside for the moment, via a limited uptake of Bergson, foregrounding images, movements and modulations in their becoming ensemble and set, I want to suggest that machine learning-based AI, especially in its increasing reliance on image data, creates certain kinds of surfaces. Such surfaces perceive or prehend the entire potentiality of images' movements by traversing particular pathways. Image ensemble, set and model coagulate to form a metastable assemblage modulated by and from the matter flux of images and by the forms of stabilisation performed in relation to these ensembles. Now, this may seem unremarkable to data scientists who spend enormous amounts of time selecting out, cleaning up, indeed aggregating images through processes such as labelling or by stabilising sets of images in order to become particular kinds of aggregates known as a training set. But it's in these stabilisations of movement extracted from image aggregates that a certain regime inflecting machine learning gains purchase. And by regime here, I mean less the imposition of pre-given protocols authorised by external criteria and more the actual acts of training of data and observers involved in machine learning. Yet, as we'll see later, the metastability of sets and architectures also suggests that new modulations of aggregates will always also arise as they're traversed. It's important to keep this aggregate image data and stabilisation training model relationality in mind when making claims about or critiquing the socio-technical politics of AI. In the light of, for example, Google Photos app assigning an image of a black person to a group of images with the label gorilla, which happened in 2015, cultural analyses of AI and the developer fix for this image recognition problem both located the model's racist gesture at the level of the image data set. So after 2 years of investigation, Google's fix for its app was simply to cease using the label gorilla to identify groups of images. And of course, this introduced a concomitant problem, which made it impossible to recognise actual images of gorillas in new images presented to the model. Likewise, cultural analyses have gone down the same path of blaming the data set. Kate Crawford, an important voice in the public domain questioning the social and political implications of big data and AI, and also a researcher at Microsoft, located this and other machine learning-driven instances of racism at the level of the data. In her words, the AI white guy issue is fundamentally a data problem because, to quote her, algorithms learn by being fed certain images, often chosen by engineers, and then the system builds a model of the world based on those images. If a system is trained on photos of people who are overwhelmingly white, it will have a harder time recognising non-white faces. However, such claims, critiques and fixes separate the image datasets out, implying that alongside a cry often heard from the big data industry itself, that what we need is just better data. Instead, what I want to suggest today is that what is at stake is the cooperation between images as particular kinds of aggregations and models as modes of training. That is, stabilisers of the movement of images along pathways that are equally enactments of certain processes of observation. Models or AIs participate in the signaletic ensemble of what Bergson calls present images. They multiply it adding new kinds of images and movements to the infinite aggregation of matter images that is, for him, the universe. They modulate this universe of images by stabilising its potential movements via very specific operations of observation distributed across many different functions and layers of computational architecture. If we want to understand how racism or any other socio-technical politics operates in AI, then, we need to begin to understand how an abstract diagram or machine is enabled, functioning not simply in the data set, but across both aggregate image data and stabilisation training model. To this end, I don't want to make a declaration about AI's pre-existing politics and biases, which, while not without validity, nonetheless elides where its actual machinic and social interfaces are being produced. Instead, I want to investigate some of machine and deep learning's more seemingly mundane operations, concentrating, for example, on the work done by algorithms such as principal component analysis, or PCA, and on image kernels in convolutional neural networks. This will help us to see how specific forms of observation are emerging as modes of stabilising or modifying the flux of images. It may also open up possibilities for thinking about where fault lines and destabilisations are also occurring. Principal component analysis, first proposed as a function in 1901 by statistician Karl Pearson, is a dimensionality reduction algorithm. It is used across a raft of machine learning tasks where multivariate or high-dimensional data makes up the data set. From the late 1980s to perhaps 2010 or so, it formed the basis of machine learning facial recognition architectures and is still used as a formative operation in these. PCA's computational success lies with its capacity to reduce the high dimensions of a given data set to a smaller data set that then represents the initial higher dimensional one, maintaining most of its information about that data set's variance. So you can think of it as the kind of JPEG codec of machine learning. In facial recognition, it uses vectoral analysis to extract the main features or principal components across the entire initial training data set, producing a significantly smaller set of images comprising just these main features, which are known as eigenfaces. It is this new set of eigenfaces that are then said to comprise a face space against which new image inputs that are unknown can be compared. I'm drawing attention to these operations because what we have here are a series of manoeuvres in which the aggregates of images as universe is being added to, multiplied and recombined in specific ways by non-human processes of observation such as feature extraction, weighting and recombination. When used in image recognition, PCA is an algorithm that in effect generates a new kind of image, one which is no longer of a subject, but rather an image that is comprised purely of information about other images. An eigenface does not picture, but rather images as vector. So while on the one hand, a reduction of dimensionality is being performed, an aggregation and modulation of the signalétic flux of images themselves is also taking place. Eigenimages extracted via PCA will show the components or vectors that are the most dominant calculative directions found in the training data set. That is, the most dominant direction extracted from the image information, but not the most dominant direction of the faces as indices of something or other. A typical component might simply be the amount of brightness or light cast over part of an image. I'll return to this point shortly. It could, of course, be argued by data scientists, and if there are any in the audience, they'll probably pick me up on this, that PCA has become a less used function in image recognition tasks since the advent and relative success of convolutional neural networks, especially the high performance of AlexNet, from 2012 onwards. Yet looked at from the viewpoint of the relation I'm suggesting is crucial between image aggregate and the setup of vectoral conditions necessary for training the model, CNNs can also be considered as more sophisticated developments of the same architectural logic of functions such as PCA. A primary operation in CNNs is the training of hidden layers of the network to function as image kernels or sets of weights trained on a dataset to detect particular features. Typically, the application of a matrix of trained weights as an image kernel to an image input extracts some aspect of a matrix, extracts some aspect of that image through downsampling. At initial layers of the network, this might simply be an edge. So, like PCA, an image kernel downsamples in order to extract weights, features, or filters that become the core of the model's capacities to detect a motif in a new unknown input image. So while both PCA and image kernels work to reduce the dimensions of data, they both produce vectors or directional ranges of values along which similarity or difference can be computed. There's a key difference between PCA and CNNs, and that is that in PCA, we might be able to actually see a visual collection of eigenfaces as a kind of representation of this surface, which I referred to as face space. However, in deep learning networks, such as CNNs, the vectoral space is the total diagrammatic movement of all the operations of feature extraction and pooling across the entire image aggregate. So it's impossible to see, and this is one really big issue for deep learning research at the moment, the impossibility of being able to see the totality of image operations in the network, or of any kind of operations in the network. This diagrammatic space is a kind of surface of constant motion, produced by both the aggregate of images and their traversal. And here we return really to this concept of the present image that's suggested by Bergson. There are two key points that I want to draw out of my focus on what seems like some very technical inquiries into the operativity of certain aspects of machine learning. Returning to the issue of how we might begin to trace a socio-technical diagram of power relations playing out computationally in machine learning, we should note first that the initial representative status of subjects of images in the case of the recognition or misrecognition of race, for example, that is, white faces, black bodies, and so forth, these issues are not primarily what is at stake here. So an identity politics that grounds itself in a commitment to better source the image data is not likely to, in itself, be entirely effective, since the image itself for machine learning is purely calculable rather than indexical. Nonetheless, the visual composition of, for example, face images in terms of brightness and contrast, foreground and background, does play a crucial role in the way in which features are extracted by functions such as PCA or image kernels. So you might want to think then what happens in a mugshot, what kind of background are people shot against, and then therefore what's the most dominant direction of difference in the image itself that's being extracted from something like a range of different mugshots. Those sorts of things are the things that count. But second, this is not to say that functions and operations such as vectorization do not have a stake in a more abstract socio-political diagram. What is crucial here are the ways in which the algorithm draws vectors through the initial aggregate of images, the training data set, to transform what Adrian MacKenzie calls the data's shape and densities. In its use in facial recognition, PCA vectorially transforms the shape and flux of aggregates into a purely calculable manifold, face space. It not only reduces the data's dimensions, but creates a new, purely informatic space across which any actual face can now be compared and recognised. The real stake here is not dimensionality reduction, but the transformation of the data, to quote MacKenzie, into something that is more like folding a pliable material. The diagram operating here across aggregates and training of both the images and the models is indeed one of facialisation, but one that doesn't function at the level of the privileging of certain faces over others, but rather, as Deleuze and Guattari have suggested, as abstractly working under two aspects. First, such a diagram produces a reference surface based on mechanisms of inclusion and exclusion. We might, for example, locate the vectoral production of face space in Pca, or convolutional layers across the entire model, filtering in and out features as operative elements, as just such surfaces of reference. The second aspect of facialisation as an abstract diagram then works to compare new images to this space. And to quote Deleuze and Guattari from 1,000 Plateaus, under this second aspect, the abstract machine of faciality assumes a role of selective response or choice. Given a concrete face, the machine judges whether it passes or not, whether it goes or not, on the basis of the elementary facial units. In other words, new image aggregates or image instances are then entrained according to a facialised regime that rests not with the visible qualities and characteristics of actual facial images, but upon a kind of invisible, smooth, vectoral surface, a hidden layer or layers immanent to the model's own computational architecture. It's the production of surfaces of reference that give away the entrainment of machine learning's emergent aesthetics to a certain process of generalisation, indeed a genericism, nowhere more visible than in the phenomenon of style transfer. Indeed, CNNs not only extract localised motifs in data via image kernels, they then often pool these motifs, correlating them across the image at another set of pooling layers within the model. Here we can see that the image is itself being conceived in deep learning research as the outcome of building compositional blocks in a direction that moves from the local toward the general, with each block hierarchically subjected to an ascending order of classes, from low-level discrimination to higher-level recognition of detailed features. And style transfer transpires as just that capacity of a convolutional neural network to detect localised motifs or style and apply these invariantly across a range of visual spaces to produce a visual generic. So thus far, deep learning's visuality at a kind of broad cultural level tends to be correlative with its own computational logic. This ability to shift progressively from local to general is also, of course, lauded as the capacity of AI at large, even though this seemingly smooth operativity belies the actual functions, processes, spatial conditioning and flux that are the contraptionalist underpinnings of such an endeavour of generalisation. However, let's not make the mistake of pronouncing this regime or diagram to be a totalising one. Its capacities for novelty, for producing different kinds of image relations, are, I think, immanent to these very same operations. Let's take the case often labelled as misrecognition, which of course has attracted a lot of public attention, the Google Photos Gorilla episode, for example, but is also fascinating deep learning researchers themselves. In a paper published in 2015, researchers reported the results of image recognition by AlexNet when run on a set of different images that they had evolved using genetic algorithms. So these were synthetic images. Here, the task for the AI was to match these evolved images to up to 1,000 classes, such as lions, motorcycles, digits, starfish, basketballs, etc., for which the model had already been robustly trained. However, in over 5,000 runs of the model on the evolved image dataset, the network consistently mislabelled the images. But I'd suggest, rather than thinking this as error or a dataset labelling problem, we instead affirm this as an instance of the model consistently performing inconsistently as it traverses different kinds of image aggregates. Importantly, the model is a discriminant analysis model, deploying low-level feature detection in an image. Here, the image labelled starfish contains the blue of water and the orange of a starfish, which featured in the original training data set. And this is something that's noted by the deep learning researchers themselves. And they say that all the evolutionary images needed to do that they'd evolved was to present to the model discriminative aspects for the model to then classify the new images as typical features of a class. So a model trained in discriminant analysis deploys exactly its training to detect low-level features in the evolved images, rather than, as the researchers say, detecting a range of features across the whole or global image. So then what the researchers interestingly conclude is that this might mean that such models are in fact not generalisable, or at least not generalisable according to a logic that starts from the local and moves to the general, a kind of inductive logic, if you will. And this proposition from these researchers is radically different than most deep learning research, which maintains and strives for generalisability. Yet in this example, the researchers also go a step further and argue that this non-generalisability might also mean that AI modelled via deep neural networks is different from, rather than matched to, or the same as human vision. Also quite a radical deep learning proposition. The question then is, do we actually want an aesthetics, or indeed a sociality or a politics, based upon AI architectures that will struggle with a generalisation that moves from the local to the general? Do we want that generic consequence, such as style transfer of an architecture entrained to a regime of machinic sensibilities, producing non-visible surfaces to which all novel instances of its creativity are then referred? Or do we want instead to perhaps acknowledge models' actual occasions of creativity, embracing a more processual conception of novelty, which sees new instances such as misrecognition and mismatched labelling as neither good nor bad, but as part of a more uneven relational ensemble and its movements? This would mean a commitment to an AI aesthetic that encourages models to run at and with their own consistencies, rather than to see inconsistency as error. It would also mean a commitment to take seriously the question of how, for example, AIs also participate in and modulate contemporary diagrams of, for example, racism. But this commitment rests upon careful attention to just how and where images and models co-compose and condition spaces for and of imaging, from the universe as nothing but images, through to modes of contemporary aggregation, through to models as observational trainers of those aggregates, through to the ongoing modulation of images' signalétic fluxes made by the actions of these new observers. Thanks very much.
So, are there any questions? Yeah, here. Okay.
Sorry, it's me again. Thank you so much for the brilliant talk and for getting so close to machine vision, machine recognition. I've been working on this lately, so I went through those models that you described. This very different from the first model to the convoluted model, right?
Yeah.
So there is a totally different modality of organization of relation between data, algorithms, the finding of patterns, you know, and how the recognition works.
Yep.
And I was struck by the idea that obviously you cannot think about this in terms of vision. Okay.
Yes.
I mean, absolutely. So
yep.
the critique of vision is a critique that doesn't work, because we are working on the if we, from the standpoint of the machine, what the machine is a kind of not just reducing like in the first model, but actually working through the numbers.
Yep. Yep.
So that is super interesting. But then I want to ask you as to how then. You know, what kind of critique we develop from there, okay? And your proposition seems to me saying we cannot just think about these models as a reduction of perception to calculation, or we need to think about in this kind of the universe of the aggregation of images. So your Bergson and Deleuze and the kind of model of the abstract is there to tell us that we need to reason, you know, we need to activate a critical introjection into this ensemble at another level, universal level. What point of view are we actually assuming there, right?
Yeah, yeah, exactly. What yes.
Yes, because and then, you know, this kind of invisibility of what the algorithm do, you know, the idea of the black box, we don't know what they're doing, so we can actually magically think that they are creating new things. But actually, if you go into the kind of literature, you see that there are models of machine learning that are activating some kind of medio topology, you know, medio topology. So the relation between parts and whole is completely different. So.
Yeah.
There's something called dynamic reasoning in machine vision, which is super interesting.
What's that? Sorry?
Dynamic.
Dynamic.
Yeah,
right. Yep,
they
yep.
use medio topology.
Yep,
like that.
yep.
So it seems the point of view we are assuming for critique is almost like we need to enter this zone of how they see, and how they see. You know, it's not just about if you are proposing that it's on the level of this massive aggregate, or modulating aggregate. Of vectors and numbers transforming in vectors, then vis-a-vis the critique of biases, or, you know, Cambridge Analytica, or this kind of idea that this system just reproduces what is already there, what we input in it, right? So how do you tackle that question?
Yes.
Of course you are tackling it at a massive scale, but...
Yeah. I mean, I think that of course, this is the question of this project in many ways. Really early stages at the moment. So for me, the first thing is to stop entering from the point of view of the question of the problem of the data, the problem of whether the data is simply reproducing human biases. And therefore creating better data, because you've already started from the outside rather than from what's going on machinically. But then the point, of course, is if you take, as you say, if you take the question of this question of dynamism and this question of kind of ongoing signaling flux, where is the point, where can you enter exactly and I haven't got a point of entry yet, except to say that I think the point that we're entering from at the moment is problematic, because we'll never get to where things are actually being produced, where there's some kind of new sense of the image being made. So you're right to point out that this is exactly the problem, but exactly where one can enter, I don't know yet. Yeah, but but certainly not from the point that's being entered at the moment. I think that's a problematic point. Yeah. Do you have it? Do you have
we can talk about
a point of entry?
Maybe. I don't know.
A secret point of entry?
Yeah, thanks. And I really liked that you pointed out that the data there is in the shape of matrices, vectors, numbers, and stuff like that. Do you see any difference, or where do you see the difference to the representation of data and knowledge in, let's say, living corpuses like humans, where current research is to the point that these things are represented in quite delicate functions of chemical and electrochemical operations in the synapses, which in some parts can be measured, which would be also in some way numbers or values? Or do you think of something like a mystic human add-on to this?
Okay, so I want to answer that in two places. I have no doubt or problem with the possibility of measuring chemical reactions, interactions, synaptic reactions, interactions in humans. But I do have a problem with the correlationist argument that says this correlates to all kinds of other kinds of behaviours in organisms. So that's one part. And the second part is that that while one can do all those things, to go back to something like the infra-thin in Marcel Duchamp, which I raised in David's talk, how would you explain the feeling of the warmth that one feels as the seat departs from one, in terms of that kind of a model? However, I don't think that that is a special thing for humans. Humans have certain kinds of vitality effects, but so do all sorts of other non-human and inorganic beings as well. So we're getting into some very complex philosophical areas as well. So I think part of the issue is that the relationship between AIs is always brought back to a relationship to the human. And if we started from a different position, we wouldn't need to worry about those kinds of things. Which is partly why I want to start from this kind of signaletic flux position, which many kinds of entities are engaged in, not just humans. So my problem is more with the framing from the start, that there's this human and then machine. Not that I find it problematic that humans are measured. I don't find that a problem at all.
Okay.